Hi, my name's Bill Harrison. I'm here to present some work that I've done on hardware assurance using ideas from functional programming and language semantics and things like that. So there's a long tradition of using functional languages for doing hardware synthesis, or at least there's been a fair amount of research in that area, and that's been going on for some time. There are some functional hardware description languages that are well known, Chisel being principal among those. The one I'm going to talk about today, at least obliquely, is called Rewire. One reason why people are interested in using functional languages for describing hardware and building hardware is that functional languages have what you might call the software engineering virtues, that is abstraction, modularity, and reusability. And there's also, people have noted some similarity between pure functional languages and at least certain parts of hardware description. Well, there are a lot of work, while there's a lot of work on using functional languages for high-level synthesis because they have software engineering values or virtues. We're interested in using them because you can also reason about functional languages, particularly languages that already have rigorous formal semantics like Haskell. And so there are a number of reasons why functional languages work for hardware assurance. One of which is, well, it's possible to give them semantics, and there are a bunch of proof tools and I would say existing knowledge that you can use to reason about functional programs. And so if those functional programs describe hardware, so much the better. So in previous work in Rewire, we described a secure dual-core system where what we did is we took picoblaze processors represented in Rewire or implemented in Rewire, and we hooked them together in a way in which we would create a dual core, and there would be this shared register, and we, not to go into the details, but we enforced a no write down policy so that the high picoblaze, the blue H1, could not write down to the low picoblaze, and the low picoblaze could only write up. So in any event, we then formally verified, that is by hand, we did a proof by hand, that this particular security specification held of this Rewire specification. And what that security specification says basically is, from Low's point of view, that's what's this thing down, this diagram down in the bottom right, says that from Low's perspective, it doesn't matter whether the high picoblaze is replaced by a do-nothing no-op processor that does absolutely nothing. And so we proved that, but by hand. So it was not checked mechanically using a theorem-proving system like Coq, for example. In any event, the details of that work can be found online. So what I'm going to talk about today is something called the device calculus. And so basically what the device calculus was designed for was as a kind of a semantic framework for describing hardware. And its main structure is basically a representation of a Mealy machine. And we represent that Mealy machine in a language called AGDA, which is a dependent functional programming language, much like Coq is. And you can do proofs in AGDA about AGDA programs. So again, you know, the details are in the paper, but there you go. So in order to represent a Mealy machine, so if you look up here at this diagram here, that's a traditional representation of a Mealy machine, where you have every cycle you have an input I, you have a internal storage S that's read, and there's some updates to that internal storage, and then at the end of the cycle you produce some output O. What this Mealy machine does, or this representation of it does, is it says, look, I construct this Mealy type constructor. It's co-inductive, whatever that means, don't worry about it. just think it means that it's non-terminating. And then at any particular cycle, we can say, if you give me an input and an internal storage, I will give you a snapshot. And what the snapshot is it's basically, it says, it just records, I got this input, my internal storage was this before I did anything, my internal storage was this at the end of the cycle, and this is the output I produced. And so this Mealy ISO becomes a type constructor in AGDA. It's a type constructor in the device calculus, and you can reason about it using AGDA. So that's what the heart of the device calculus is this first-class representation of what a device is. So in device calculus, as I mentioned, devices are first class. That's why it's called device calculus. So device calculus is a kind of lambda calculus. Again, this is all sort of language nerdism that we needn't go into, but if you're interested, it's a kind of lambda calculus, or a functional language, in which devices are first class. So for example, you have an operator like a parallelism operator that says, if you give me D1 and D2 that are both devices, aka Mealy machines, then here's a way that I can set them next to each other and so that they execute in parallel. And so there's some other operators that we define. We won't go into them in any detail in this talk. There isn't time, but there's more information in the paper. So anyhow, so this is the device calculus. It's a lambda calculus in which devices are first class. So just as another example, we can take a declassifier diagram. So this is a diagram that I took out of a famous paper by John Rushby, who's a well-known formal methods and security guy, describing what a downgrader or declassifier is. And basically what it says is, look, you have these, in effect, devices, and the arrows indicate the direction that information can flow. With a downgrader or a declassifier, information is allowed to flow from secret down to unclassified, but it must always go through the downgrader. Now, in device calculus, we can express this as a function. Now, what we do is we have these three device parameters, and we put them in parallel, and then we connect them somehow. Again, the details are in the paper. But the precise meaning of what this function is isn't necessary to understand, other than to just say, look, this is a way of defining, given three devices, a way of connecting them in a particular way that corresponds to declassification. So to return to the original example from the Rewire secure dual core, what we can do is use device calculus to then specify that system in device calculus. Again, just like in the previous example, we can easily define it as this particular function, and then because it's written in AGDA, we can use AGDA to reason about it. And that's what we mean by saying that it's a verifiable security template. It's verifiable because it's all encapsulated in AGDA, and it's a template because it takes these devices as parameters. So here you're now taking low and high as parameters. So this diagram is very similar to the one I showed 2 slides ago. So for conclusions and future work, I reiterate that this is a work in progress. So it's particularly called verifiable security templates. So we're working now on actually verifying these templates and showing that the templates preserve these security properties. That's different from saying that they are verified. So when we our follow-on work, when we do a more rigorous kind of formal methods presentation of the device calculus, we will show the verifications as well. And so in particular, we're interested in replaying the proofs that we did by hand in our work from 2017, and verifying those or encoding them into AGDA and checking those proofs. We had a previous paper last year where we wrote a semantics for rewire in Calc, and in part this work is a response to our own work, where we were the thing that we really liked about AGDA was that we could much more easily encode co-inductive structures, that is non-terminating structures, than we could in Calc, which we could certainly do, but it was more challenging. So one thing that we're also looking at as an application of device calculus is as a semantic substrate for Fertile. Now, if you're familiar with the Chisel environment, the Chisel tool set, Fertile is this intermediate language that it's a small intermediate language that is targeted by Chisel. And Chisel is written in Scala, and there's no semantics of Scala likely to occur. But Fertile itself can be semantically specified, and so that can give us access to formal methods by looking at Fertile modules. It also will give us a framework for sharing Fertile functionality with other HLS tools. I want to thank you for listening to me today.